My 15 to 51 final project is about authentication and blockchain. So I'll be presenting in an order of preamble, authentication and encryption algorithms, types of authentication, blockchain and zero-knowledge proof, and end with conclusion. So preamble. So why should we care about authentication? Why would this entire topic matter? Well, first of all, authentication is used in so many ways in our daily life. For example, we would use it to identify ourselves, to do bank-related or document works. We would also need to verify that it's ourselves in order to use our credit card info for online shopping, or in order to just access our accounts, our social media accounts. And it would be crucial to keep our information safe and secure through authentication so that other imposters can't pretend to be you and access your data. So with authentication, you will be able to continue using your online services safely. So the goal of this project is to understand the importance of authentication, different types of authentication algorithms, zero-knowledge proof, and the role of zero-knowledge proof in blockchain. So the first part would be on authentication and encryption algorithm. So what is authentication? The formal definition of authentication is the process or action of verifying the identity of a user or process. So for example, if person A wants to use the service would then ask person A to provide that they're themselves. And through authentication, person A can provide that they're themselves, their identity, and access the service. Cryptographic systems we learn in class often use exponents and modular arithmetic as an encryption algorithm. For example, Diffie-Hellman secret key exchange or RSA public key cryptographic systems both use exponents and or modular arithmetic. But there are other encryption algorithms as well. There is message digest algorithm, called MD5 for short, that given a message, it outputs 128-bit message digested using hash function. There's also data encryption standard, called DES for short, that outputs 64-bit blocks using 56-bit keys. And there's skipjack, which is similar to DES, that outputs 64-bit blocks, but it uses 80-bit keys instead of 56-bit keys. The first is password authentication. It is the most commonly used authentication around the world, and it could divide into two different ways depending on the duration of the validity of password. So if the password expires after a single access granted, it's called one-time password, versus there's reusable password where you would use the same password in order to access the server. The way password authentication works is by the system storing user ID and password in a hash table, and it uses modular arithmetic to hash into the hash table. And there are various ways to do it, called salt and pepper. So salt is storing additional randomized string that would be attached after to the user's password. So there are people out there who would set password to something that's common, for example, 1234, or just password. And that wouldn't be as secure if there are multiple people just setting their password as password. So what salt does is it also generates randomized string that will be attached to the user's password, and the system will be saving that additional randomized string as well to the table with the user ID and the password. And every time the user would enter in their ID and password, the system will be looking up the user ID and see if the hash value, when given an input of password and the additional randomized string, if that equals to the hash value, it would grant access. Pepper is similar to salt, but it adds the same secret string to each password. So the main difference between salt and pepper is that salt generates new randomized string for each user ID and password, while Pepper will be just adding the same string over all the passwords, but it's maintained in secret. Initially, there was also a critical drawback to password authentication because some malicious person could just enter in random string and then semicolon and then like delete table, for example, which would then make delete table run as a code instead of part of the password string. And if the code is run, for example, the delete table, it would delete the table and it wouldn't do any good to the service. But nowadays, all websites have protections against it from happening. The second authentication is key authentication, and you could think of this as a method that utilizes one-time password. So it provides one-time password for a certain number of access. So it would provide, for example, if the administrator wants to grant n number of access to the user, they would be providing n number of one-time password for the user to use. And this authentication method relies on one-way function, for example, x raised to a mod b, which was used for RSA. And it would recursively apply the function to a random initial value, for the number of access granting to the user. And the way it would work is, you could think of it as like an onion. So you will be peeling each layer every time the access is granted. So every time the user enters the password, the system will then apply the function to the password and then see if that output equals to the data stored in the system. And if they equal to each other, then the system will be replacing the previously stored password with the new password entered and then would grant access to the user. So it's basically crossing out the number of access every time the user inputs the password in order to access the service. The third authentication method I want to introduce is Kerberos authentication. In Greek mythology, Kerberos is a three-headed guard dog that prevented dead souls from leaving through the gates of the underworld. The name Kerberos of this authentication was obtained from the 3 layers of servers a user has to go through in order to be authenticated. So the 3 servers are called Authentication Server, Ticket Granting Server, and File Service Server. So we'll be calling Authentication Server as AS and Ticket Granting Server as TGS. AS and TGS together are called Key Distribution Center, or KDC. The way Kerberos authentication works is through 3 sets of shared keys. So the user and AS would be sharing a key, and AS and TGS would be sharing a key, and TGS and the server would be sharing a key. So first, the user will be sending encrypted requests along with their ID to AS asking for a ticket to a service server. Then AS will be decrypting the encrypted request using the shared key with the user. And once the request is decrypted, that would verify that it is the user who sent the request. And once AS verifies, AS will be sending the user a ticket granting ticket, or TGT for short. And with the TGT, the user will be sending it to TGS. And with the shared key between AS and TGS, TGS will be decrypting that ticket granting ticket. And if it's valid, TGS will grant another ticket to the user, which is encrypted. And lastly, user will be sending that ticket to the service server, and with the shared key between TGS and the service server will be decrypting that ticket. And if it's verified, the service server will be granting the user access to the service. The last authentication method is blockchain authentication. And the way it works is by using blockchain. The general idea of blockchain authentication is by proving oneself through one of the blocks in the blockchain. because of the way blockchain is constructed, it is hard to change an information inside a block once it's verified. So the way it works, the way blockchain works, which I will be explaining it more in detail in a few minutes, is through hashing. So whenever someone wants to add a new block to the blockchain, it would first create a hash value for the block, and it will be sending this new created hash block to all the other computers, because blockchain is decentralized system, meaning that no one computer or a system overtakes the entire data of blockchain. So because it is spread across multiple computers, it would then need to send this newly created hash block to all the other computers, which are called miners. And once all the other computers also confirm, then it is officially added to the chain. And blockchain authentication, the main benefit of it is that it is a non-destructive way of keeping the record. So whenever someone wants to alter some information already inside the blockchain, they would then have to create a new block indicating that they are changing certain information from this old block that's already part of the blockchain. And because the way blockchain is constructed, blockchain ensures that the data is accurate by just presenting that it is part of the chain. So now moving on to blockchain and zero-knowledge proof. So I'll be explaining more about blockchain in depth. So what exactly is blockchain? Blockchain system is basically a chain of blocks, of which each block would be comprised of data, hash, and the hash of the previous block. So you could think of the way it is hashed is like this. So because it also includes the hash value of the previous block, it would then have to hash the hash value of the previous block, resulting each section of the hash value to look like that. And because it is constantly hashing over and over recursively, it is hard to alter a block that's within the blockchain. So for example, let's say someone wants to alter an information in a block. Then because the data part of the block is altered, now the hash value for that block also changed. And because of that, all the following blocks would be having their hash value change as well, because part of their hash value includes previous block's hash value as part of their input. So now if this happens, we need to recalculate all the hash values. But with developed computer power these days, that's no problem. But so in order to prevent just changing part of the block and recalculating over and over, there is this thing called proof of work. So across multiple computers, it's basically setting some time limit for each recalculation to happen. So let's say, for example, it has a time limit of 10 minutes. So every time each block has to be recalculated of its hash values, it would take 10 minutes, even though the actual calculation would not take for that long. And because of proof of work and hashing aspect of this blockchain, it would make blockchain very secure and accurate. So then why should we know about blockchain? Like, where is it being used? The main usage is in cryptocurrency or Bitcoin. Because cryptocurrency isn't necessarily owned by any country or what is governed by any system. It needs a way to keep track of all the transactions that's occurring, and the way it records the transaction that occurred is through blockchain. Blockchain could also be used for recording paperwork or medical records, or it could be applied in owning artworks in a similar sense of owning stocks. Then what is zero-knowledge proof? Zero-knowledge proof, for its formal definition, is a method which the prover can prove the verifier that a certain property of the information is true without revealing any other information apart from that the information holds the certain property. So the prover will be proving to the verifier that they know something without telling explicitly what that something is. So an example would be this bits. So imagine you have 2 bits. It could be either 0 or 1. And the prover will be saying that, oh, the 2 bits are different. But the verifier wouldn't believe it because the prover could just be lying. And in fact, it could be just like 0, 0 or like 1, 1. So the verifier will be testing prover to ensure that prover indeed does know that the 2 bits are different. And the way verifier will be doing this is by hiding these 2 bits behind the verifier's back and then like either swap or not swap. And the prover would not know whether verifier swapped the 2 bits or not. But whenever verifier presents the 2, the prover can say whether the verifier has swapped or didn't swap these 2 bits. And if they conduct this test for like 100 times, for example, there's a very small chance for the prover to get everything correct by coincidence, by just guessing. So by the time multiple tests has been conducted, verifier would be more convinced that prover indeed knows which one is which, or like the fact that the prover knows the 2 bits are different. Another easier example would be utilizing finding Waldo. So the prover can say that, oh, I know where the Waldo is, but it'll be no fun if prover can just point at Waldo. Then verifier would do no work to find where Waldo is, but would know the answer directly. But verifier could be skeptical about the fact that prover indeed knows where Waldo is. So the verifier could ask prover to prove the fact that prover indeed knows where Waldo is. And the way prover could do this is by presenting a cardboard that is 4 times bigger the size of the book. And there will be a little cutout of Waldo in shape of Waldo in the middle of the cardboard. And the prover can place the book behind the cardboard such that it shows where the Waldo is. But because the placement of the book could be anywhere behind the cardboard, the verifier will not know where exactly Waldo is, but would know that prover indeed knows where Waldo is. So zero-knowledge proof proves that the prover knows certain fact without having to reveal more information about it. And zero-knowledge proof has these 3 components. First is completeness. So if the prover tells the truth, then the verifier will be convinced of this. And this could be done by conducting multiple number of tests, or the prover just proving. For example, in that Waldo example just now, the prover can just show where the Waldo is with the cardboard in front of the book. The second is soundness. So if the prover is lying, then the prover cannot convince the verifier that it is true except with some very, very small probability. So this ensures that the prover is telling the truth. The last component is zero knowledge. So if the prover is telling the truth, then the verifier will know nothing more other than the fact that prover knows the fact that they're saying. So then how could this zero knowledge proof used in blockchain? Let's have an example of transferring money. Say you want to transfer some amount of money to another person. If you send it through like Bitcoin cryptocurrency, all the transaction information remains public and other people can see how much has it been sent from who to whom. If you send it through the bank, yes, I guess it remains private, but the information is kept centralized. So if someone wants to change an information within the bank, then they could just alter it and there'll be no other proof to show that the information has been altered. So then how could we use zero-knowledge proof to take the best of both worlds? Zcoin is an example that uses zero-knowledge proof in blockchain to keep data private. So the way it works is like this. The sender would first send the money into the set. So it would think of it as an account, a shared private account that the sender would put money into. And then the receiver can use zero-knowledge proof to prove that's themselves, to authenticate themselves, and withdraw from that set. And this way, the more people use such transaction method, the bigger the set would get, and it would make the information more private because they wouldn't know exactly who's sending money to who. And also, no other further information would be required in order to authenticate themselves or identify themselves because they would be using zero-knowledge proof, which would be only proving that it's themselves without having to reveal more sensitive data like social security number. So with zero-knowledge proof, we can decentralize and keep privacy. So the conclusion is that through this project, we just went through the usage of authentication to keep data private, different types of authentication algorithm, namely password, key, Kerberos, and blockchain. We also talked about zero-knowledge proof and its application in decentralizing data and maintaining privacy. Thank you.